Hi everyone, today I'll be discussing our recent work called Safe Reinforcement Learning with Probabilistic Control Barrier Functions for Ramp Merging. I'm Soumith Udatha. Yiwei is our PhD student and Professor John Dolan. We're from Carnegie Mellon University, Pittsburgh, and we're presenting at the AI480 workshop IJCAI 22. The outline of the talk today is we first set up the problem, and then we discuss the preliminaries and related work. Then we go through our proposed method, some of the experiments we ran, and the results observed, and also a slight discussion on the future work we're planning for this project. Ramp merging scenarios are possibly one of the simplest scenarios for autonomous cars to learn behavior from one-on-one interactions. They're usually encountered in highways and where a vehicle on ramp has to merge onto a lane onto the main highway. The image on the right clarifies some of the notations that we use in this presentation. The vehicle on the highway in green is referred to as the host vehicle that we do not control and adjust our behavior to. The car on the right, already on the ramp, and is trying to merge in red is our ego vehicle that we control. This bar plot from NHTSA, National Highway Traffic and Safety Administration, shows the number of fatal car crashes on the US highways. Although the trend keeps going down for utmost safety, we should still ask the question of why these crashes keep happening to understand the human driving behavior, to make it easier to transmit this information to autonomous cars, which we want to be prepared to almost all of the driving types encountered on highways. In this plot from NHTSA again, we just look at the crashes in the year 2019, most recent year for which the data is available, and look at the damage caused by car crashes. They mostly result in property damage, physical injuries, sometimes lifetime ones, and ultimately fatal crashes too. Although being a simple driving scenario to model, ramp merging scenarios are still very high risk areas for motor vehicle crashes due to the variety of human driving styles at high speeds. Humans also introduce uncertainty to merge scenarios, and autonomous cars might collide too if they're not prepared for this uncertainty. Now let's look at some of the preliminaries and related work in this area. Starting with the standard reinforcement learning problem, we have an agent taking an action A in the state S of the environment to transition to a state S prime and get a reward R. The RLI agent tries to maximize the expected reward that it will get out from the environment. Then we have control barrier functions defined for non-dynamical systems that have provable safety characteristics, given an admissible safe set and a safety condition. So CBFs with provable safety, why can't they solve the problem of autonomous driving, or at least a simpler case of ramp merging? It boils down to the complexity of model compression and specification in high-dimensional spaces. Real-world environments also have frequent and we need accurate models to capture real-world dynamics. Specifying safety functions for high-dimensional complex spaces also becomes a challenge. Combining RL methods with CBFs might prove a stronger combination to tackle these problems. Some foundational work in this regard is that of constraint policy optimization, where an MDP is further augmented with auxiliary costs for the constraints involved. For each policy improvement update, we satisfy the constraints of the environment, trust region constraint, while maximizing the objective. To embed CBFs into this approach, we use them as constraints of the optimization problem. Using plain CBFs might still not mitigate the problem of model uncertainty involved with control barrier functions. So one of the prior methods I've used the concept of generalized control barrier functions, defined for discrete time control barrier functions with higher degrees of freedom systems. The authors then combine the generalized control barrier functions with the CPO framework. Let's build upon these concepts to set a footing for our method now. The dynamics model we deal with is slightly different to the ones considered in prior work. We're also dealing with ramp merging as a two-dimensional problem. Prior work has addressed ramp merging as a one-dimensional problem. We consider both the dynamics in X and Y disentangled into two different separate quantities, and also include the uncertainty involved to deal with probabilistic control barrier functions that we'll be dealing with in the next slide. Probabilistic control barrier functions are a novel variant to deal with models with uncertainties. Probabilistic CBFs plan for a certain level of uncertainty in the environment. We use the dynamics formulation in the previous slide to obtain the probabilistic CBF constraints for a ramp merging scenario. The probabilistic chance constraint is further reduced to a linear set of constraints to be used with the CPO framework. The flowchart here resembles the pipeline we've used for the SafeRL algorithm. We start with an initial state distribution, a culmination of rollouts we collected. The initial state is not a safe state, We reset the simulation to start from the same state. The agent takes short rollouts from the policy, and the agent resets to another state from the initial state distribution to take another short rollout to form a set of trajectories at random locations, which are then passed to the optimization framework to improve the policy. Here we look at the optimization framework called Safety Assured Policy Optimization for Ramp Merging, SAPO-RM in short. G is the expected cost of the policy in the environment. We also have control limits on the variable U, that is the throttle of the car. And then we have auxiliary costs JCX and JCY in the X and Y dimension respectively. The probabilistic CBFs are narrowed down into the matrices AEMX, AEMY, and vectors BEMX and BEMY for the disentangled controls UEX and UEY. We also have DP, which is the trust region constraint, defined on H being the Hessian. Combining the elements of the previous slides into a concise form, we arrive at the pseudocode of the algorithm. This has a similar framework of converting the optimization to its dual and solving it, as also seen in the CPO framework. And when there isn't a feasible solution, we look at the line search criterion. More details about the algorithm are mentioned in the appendix of our paper. Let's discuss how we set up our environments now on CARLA and on an NGSIM database. On CARLA, we ran a search for the possible predefined environments to find a ramp merging situation. Towns 4 and 6 are the ones with highways, and we narrowed down to the following ramp merging shown in the image in town 6. As you can see, the ramp is curved. Although we are controlling the car in X and Y dimensions, we are still just controlling the throttle and not the steering of the car. So for this approach, we assume the steering of the car to be decided by an inbuilt PID controller that plans between waypoints to reach the goal waypoint. The control for the merging vehicle is also modified to use the PID control in both lateral and longitudinal dimension. Further, the control of the merging vehicle is agnostic to the behavior of the ego vehicle. And so in this environment, we have a case where the ego car is controlled with the policy, whereas the merging car is controlled with the planner, and we observe the behavior in this context. For the experiments with the NGSIM database, we are considering the US I-80 highway data. There are 7 possible lanes in the NGSIM database, and we are only considering the trajectories where a merging is observed. We find merging to be the transition from lane 7 on ramp to either the auxiliary lane, that is the lane shared by both off-ramp and on-ramp, and the transitions from ramp to the merging. In the image shown in the slide, the trajectories in blue highlight the merging trajectories, and trajectories in black highlight the corresponding ego vehicle trajectories. We arrived at these trajectories by narrowing down to a merging condition which was based on distance and where one-on-one interactions are observed. We also modified our algorithm to an offline SAPO-RM case to work with this environment. Let's look at the results of our algorithm on these environments. Here, we look at the case with a conservative value of alpha for the red car, and where the host vehicle moves with a velocity of 20 km/h. The ego vehicle is conservative to the ramp merging scenario. The ego vehicle waits for the host vehicle to pass and then merges behind it. The safe RL algorithm also exploits the environment reset for a merging vehicle, in addition to the safety involved. Let's also take a look at the plots. In all the experiments done, we have a safe distance of 8 meters. From the distance plot on the left, we see that the safe distance is maintained. From the ego control plot, we see a case where the throttle control goes to full braking until merging is resumed, and then goes back to full acceleration to get back to the merging process. Now let's also observe a simulation result where the CBF alpha parameter is more aggressive. In this case, we observe that the ego vehicle merges in front of the host vehicle, taking an aggressive maneuver. The host vehicle has the same velocity as in the previous vehicle, 20 km/h. This change in behavior is mainly attributed to the difference in hyperparameter of the CBFs involved. Looking at the distance in ego control plot again, we see that the distance condition of 8 is still observed despite the aggressive behavior. The ego control is on average to the full throttle as we calculate. As we observed in the case with a lower alpha parameter or a more conservative parameter for alpha, meaning the behavior of the car is more instinctive now. With the safe RL algorithm we have trained in the offline condition in the database, We roll out the policy on the test data distribution. The snap of the rollout is shown in the slide. We can observe there are three different trajectories in this image. The trajectory in green is that of the ego vehicle in the dataset. The trajectory blue is the merging vehicle from the dataset. And the trajectory in black is that of the train policy for ego vehicle. The trajectories for all the three are rolled out for time instance. In this experiment, the minimum distance between the green trajectory and blue trajectory violates the safe distance at 5, but the ego vehicle, being trained to maintain the distance, speeds up its position on the trajectory and maintains the safety condition. For the experiments on the NGSIM database, there could be possible options to fix the heading angle of the car. In our policy, we were using a case where the heading angle of the ego car is the same as the ones for the ego vehicles in the dataset. Here is a zoomed in version of the trajectory shown in the previous slide. In the previous slide, the scales for both x and y dimension are not the same. And while zooming in on the x dimension, we have our trajectories more clearly, and the ego vehicle trained is not taking sharp trajectories, it's just an illusion of scale. Let's talk a little about the possible future directions of our project as we come to the end of the talk. For future directions, we look at performing thorough experiments in qualitative analysis with various possible variants of CBFs to model the uncertainty, experiments to observe the variations in driving behavior with hyperparameters of the control barrier functions, if possible also to extend to merging scenarios with multiple vehicles and complex maneuvers of lane cutting on highways. Now, we further thank the reviewers for going through our work and accept any comments, questions related to this presentation right now. Thank you.